Hi. Yesterday we learned how we can derive a covariance formula, conceptual formula, and also how we can derive correlation formula, Pearson correlation formula using the conceptual covariance, right? So covariance is the association between two variables, right? Covariance formula is really similar with the formula of variance, right? But the difference between covariance and variance is a univariate value, right? Just only about x. Covariance is a value between two variables, right? Okay, so the correlation is the standardized covariance, correct? Okay, so today the topic is regression, linear regression. Regression is more advanced than correlation, right? Because correlation coefficient just tells us the strength of the relationship between two variables, right? And the relationship had three kinds of elements, right? So number one is strength. Number two is direction. Number three is shape, linear or nonlinear, right? But we do not decide in terms of the correlation coefficient. We do not decide which one is a predictor between two variables. We do not decide which one is outcome variable between two variables. But regression consists of independent variable and dependent variable. Independent variable is called as what? Predictor, explanatory variable, independent variable, right? X variable. And Y variable. Y variable is called outcome variable. Criterion variable, right? Predicted outcome variable. Okay. Okay, so record the shape of the relationship being modeled by the correlation coefficient is linear. Okay, so correlation index is just generated by, SPSS, a statistics program, but that doesn't mean the relationship between X and Y is linear. Correlation index, correlation number is anyway generated by the machine, assuming the relationship is linear. So assumption means what? Assuming. Assumption means just assume, regardless of it is true, right? True or not. So what we want to do is, before we compute correlation index using SPSS, we need to look at the scatter plot between X and Y to see if it is linear, right? If it is not, we should not use the correlation, right? We have to do something special treatment, in that case. We're gonna touch that procedure a little bit later. But anyway, let's say the relationship between X and Y is linear. So we're gonna use correlation. And now, once the correlation index is pretty high, you wanna see the literature between two variables. So which one is which variable functions as a predictor and predicted outcome respectively. So theory tells that relationship, and then you decide one variable as a predictor, X variable, and the other variable is Y variable, okay? When you have only two variables. So So once you decide one is the predictor and the other is outcome variable, this is a simple regression. Okay. All right. So R is, what is R? Correlation, sample correlation, statistic, right? Alphabetical letter R is Pearson correlation in the sample data, sample statistics, right? And what is the parameter? What is the population parameter of a correlation? We use Greek letter, right? Greek letter. When you indicate population parameter, which is true value, but we never know, right? That parameter is called what? Row. Okay, so row. And alphabetical letter R is a statistic in the sample data, right? R, okay? So R describes the degree to which a straight line describes the values of the Y variable across the X range of X values. If the absolute value of R is close to 1, so that is a strong R, right? Because maximum value of R is 1. Then the observed Y points all lie close to the best fitting line. As a result, we can use the best fitting line to predict what the values of Y variable will be for any given value of X. To make such a prediction, we obviously need to know how to create the best fitting line. So as known as regression line, best fitting line is a regression line, okay? So, this is just a regular, equation, y equals mx plus b. So we just switch the some words into regression form. Conventionally, we use y equals b0 plus b1x. So instead of m, or instead of m, coefficient, instead of m, we use b1, and the constant or y-intercept b, in the equation y equals mx plus b. So b is y-intercept. What is the definition of y-intercept? When you plug 0 in the x, the value of y is the y-intercept. So b is y-intercept, right? In the equation y equals mx plus b. But we usually use b as b0 in the regression line, and m is used with b1. So if you add one more x variable, you will use the coefficient for x2 as b2. Like for instance, y equals b0 plus b1 x1 plus, if you have one more x, which is x2, you will have a slope or x2 coefficient as b2. So like this, y equals b0 plus b1x plus, is this working? Oh, it's not working. Okay. I just tried to use a graphic pen, but it was not working. Anyway, y equals b0 plus b1, x1 plus b2, x2 plus blah, 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 depending on how many x variables you have, right? And then, like, let's say you have a number of k, so blah, 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 b, k, x, k, things like that, right? Y equals b0 plus b1 x1 plus b2 x2 plus b3 x3 plus blah, 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 until bk xk, things like that. Number of k x variables there, right? So if you have more than 2 x variables, it is called multiple regression. But we have only one single x variable here, sorry. It is called single variable regression or simple regression, okay? So we need to show whether y is an actual score or our estimate of a score. We will put a hat. So whenever you see hat on the top of y, that means estimated value or estimated line, not the real value of y, not the observed value y. Hat means estimated, calculated, expected. Okay, hat means estimated. Okay, so y hat equals b0 plus b1 xi. So here I is individuals. Let's say you have 300 students in my class. I mean, I have 300 students in my class, for instance. Then from number one student, let's say Brian, Brian's ID is 1, and Rachel's ID is number 2, and Jiwon's ID is number 3, something like that. And then 300th person student, let's say 300th student is J, then J, XJ, like that. So everybody, 300 persons, X values are different, right? Well, it can happen to be the same, but it's not necessary, right? Everybody have their, everybody has his or her own X scores, right? Yeah, that's the actual value, okay? And also whatever it is, if there is a dependent variable y also have a 300 score, right? So J's y is different, Jiwon's y is different, Brian's y is different, Rachel's y is different, right? So whenever you see, data set, the structure of data set, like, one in the Excel, let's imagine that one column, first column is ID, the second column is X scores, and third column is Y scores, and the the first row is variable names, right? And the second row is ID 1, Brian, and the third row is what? The other row is second person's, right? Rachel, X and Y score there. And the third person is Jiwon. Jiwon is third person, so fourth row, right? And then blah, 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 until how many? 301st row will be J's score, X and Y, right? So based on 300 pairs, X and Y, the score, you can generate a best fitting regression line. The regression line is called y hat equals b0 plus b1 xi. All right, so, but, this is estimated line, right? So actually you plug Brian's X score in this regression line, the Y, actual value of Y from Brian will be different from Y hat, calculated value, Y hat. Coincidentally, the two values, Y observed value and Y hat value, could be the same, but not necessary. It's not guaranteed, right? So what I'm going to say is here, Y hat equals B0 plus B1 xi. I is people, right? 300 people. So I the 300, let's say so. Then this is called estimated line. And what about the observed value? everybody has a different observed value, right? 300 people's observed values are different. So in that case, yi, just yi. And the yi can be from 1 through 300, right? So y1, y2, y3, y4, something like that. So yi equals b0 plus b1 xi plus something, right? Because there must be some kind of difference between actual value and estimated value, right? So the difference between actual value and estimated value is called error, an error, okay? An error or residual. Some people call residual. Some people call that residual, okay? All right. So I said, you'd better memorize these definitions, but you don't need to. Once you read these concepts and if you can understand that, you don't have to memorize these definitions. Just read these definitions repeatedly. Then I think automatically at some point you can naturally remember them. I hope so. Anyway, the fitted or estimated regression line is y hat equals b0 plus b1 xi, where y hat is the value of y estimated or predicted by the linear model for case I. So case I means it can be Brian, Rachel, G1, blah, 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 until J, right? So B1 is called slope. So what is the slope? Definition of slope. In the equation, it is defined as the change in y hat associated with a 1 unit difference in x. Okay. So if you plug 1, b0 plus b1 is y1 value, estimated value. If you plug 2, let's say just 2, b0 plus b1, 2 times 2, the y hat, the value of the second, the value. We don't know if it is just 1, 2, 3, 4, 5, 6 like that. X value can be over here, just the 1 unit difference associated with 1 unit difference. So yeah, 1, 2, 3, 4. And then whatever calculated the y value. B0, I said x is equal to 0, then the y value is the y-intercept. Xi is the x variable predictor. We refer to equation like y hat equals b0 plus b1 xi as sample or estimated regression equation. So y hat equals b0 plus b1x. This is estimated regression equation. Also, this estimated regression line is generated based on sample data. So this is estimated regression equation. There are several other versions of the model. The one above represents the predicted scores, but we can also write the model in terms of the observed score. Yeah, here. You can deduct this value from here, right? So yi minus y hat. So you cancel out these guys, right? What is the left? Yeah. E is error. Okay, error term, an error term EI. So you have 300 students. Then how many errors? 300 errors. 300 errors, right? Because from the one single best fitting regression line, from Brian to J, everybody's score is deviated from the regression line, right? So you have 300 errors. So here, these two thing is same as this, right? So you plug y hat here. And then y equals y hat plus e, right? So the first model, this is line, the regression line, okay? When you have error in the equation, error term here, these two have error terms, right? The two equations are equation for the points, each point. So points means what? Each person, in this case, in this example that I made, Brian, Rachel, G1, blah, 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 the third 300 person, J, the points that fall around the line. So here, maybe here, Brian, Rachel, G1, J, right? So based on this chunk, the chunk of dots, the machine, SPSS, calculated the best fitting regression line. So regression line doesn't include error term. And each dot has 300 error term like that, right? In the coordination. What do you call these dots? Scatter plot. So you see this is linear, right? Okay. So this line is a regression line. Basically, a regression line is computed based on correlation. Correlation, before we calculate correlation index, what do we need to do? We need to look at the scatter plot. Why? Because we need to check if it is linear. If it is not linear, we cannot use correlation. Since the regression is based on correlation, if we cannot use a correlation, if because of that is not linear, then regression is not used either. This is very, very important. That's why before we use regression, we have to check the linearity assumption. We need to check if the relationship is linear. If the relationship is satisfied in terms of the linearity assumption. Linearity assumption, okay? So we will have a variety of notation. Yeah, notation is all about sophisticated mathematical things, but don't worry about it. That's just the promise that some people made before. What we want to know is read the legend, the promise first, which one indicates which one. Then we just plug that into our scheme that we just learned. Y hat equals B0 plus B1, X1, just like that. So there's no difficulty at all, I promise, okay? There's no math issue. Don't worry about the math. Statistics, especially this is social science statistics, applied statistics, does not necessarily very in-depth mathematics. We just need a little bit, just math, algebra, linear algebra, that's it. So don't worry about it. Maybe a little bit later, when we learn logistic regression, logistic means logic, it's from logic. So logarithm, function. Yeah, there is a little bit math, but don't worry about it right now. We don't go through exponents or logarithm right now. So we just need a little bit linear algebra right now. So don't worry about your math, okay? We just need a little bit diligence, okay? Yeah, okay. I use hat over y to indicate an estimated score, okay? Y hat is indicated, estimated y. Okay, my slide will differ somewhat from the book's notation. Don't worry about the book notation because we don't use the original course designer's textbook. I provided my ebook. Yeah. Yeah, in that ebook that we use the same notation. Okay. Anyway. Okay, one is that our book uses a lowercase. Okay, don't worry about this one. Okay, don't worry. We also use the head over Greek symbols such as beta to indicate estimate of population parameters. Yeah, we we used to use Greek letter because of the coronavirus, right? Alpha, beta, gamma, epsilon, omicron. Anyway, one confusion we will need to deal with later concern beta weights. Okay, I'm going to talk about beta weights a little bit, not a little bit, much later, not now. Right now, you don't need to know about this one, just what you remember is this one sentence. We also use that head over Greek symbols such as beta, indicate estimates of a parameter. Population parameter uses Greek symbols. Sample statistics uses alphabetical level. Okay, alphabetical level. For instance, B. Greek symbols in population parameter is beta. Sample statistics is B. So this last three lines, 3 or 4 lines, I will get to the point, and then I will explain this beta weight and standardized coefficient at that time, okay? B star. So right now, it doesn't matter, okay? Don't worry about this part. Our task is to identify the values of B0 and B1 that produce the best fitting linear function. That is, we use the observed data to identify the values of B0 and B1, minimize the distance between the observed values, Y, and the predicted values, Y hat. But we cannot simply minimize the sum of differences between Y and Y hat. Why? Because when you saw the scatter plot just before, you saw there are plus errors and there are minus errors, right? So in that case, if you just sum them up, it turns into 0, right? So the sum of the residual becomes 0 because it is best fitting line. So in order to avoid making 0, in order to know the magnitude of amount of the error, what you're gonna do is you make it square residuals. So to solve this problem, we take the same approach used in the computation of the covariance or variance, right? So at that time, numerator, when you calculate variance, numerator, it was squared, right? Before you use, large capital letter sigma sum, right? We find the values of B0 and B1 that minimize the squared residuals. This solution is called ordinary least squares solution, as known as OLS regression. So today's keyword is OLS regression. Our estimation technique is called OLS. So I think if somebody asked me, okay, so if I had to choose the most important keyword of PAD 6701 is OLS regression. Boom. Okay. So we know B equals B0 plus B1 x1. This is a general form of regression equation, right? And you move B1 x1 in the other side, then turned into the negative sign here, right? And then you plug the mean values of x. X bar is mean x. Y bar is mean y. So you plug the mean values of x and y in the general form, it turned into this way, right? Okay. And then this is the formula of B1. B1. This is a computational formula, and this is last time we learned this one. Do you remember that? Last time, did you remember that? Last time we remember correlation formula. We learned how to make correlation formula from covariance, right? So covariance is SXY covariance, and SY is standard deviation of Y. SX is standard deviation of X. Anyway, you don't need to worry about this guy. It is just what you need to know is the concept of the numerator and concept of the denominator. That's it. So covariance divided over S square means that what is this one? Variance of X, right? Because the square rooted value is standard deviation. So this is a square. So this is a variance of X, okay? This guy is the same as this guy. What is this? Correlation. Correlation between X and Y, multiplication here, times standard deviation of Y equal divided by standard deviation of X. So therefore, okay, you don't have to remember this one. Conceptually, as long as you understand this one, just move on, okay? You don't have to memorize it, just move on. We just apply our concept to real analysis, the practical analysis, so you don't have to worry about the mathematical things. This is just the process only, okay? Don't worry too much. B1 is slope. B1 equals RXY. R is correlation times standard deviation of Y over standard deviation of X. Okay. I think the slope is slope. X-axis, Y-axis, and slope. Slope. Do you remember that? Slope. So slope is the multiplication between correlation. This is a regression line, the slope of regression line, okay? Regression line. Okay, so slope of regression line is derived from correlation and multiplication of correlation and standard deviation of Y divided by standard deviation of X. That's it. So let's see. If slope is getting bigger, what do you think? There is a tendency SY, standard deviation of Y is bigger because this is numerator, okay? What about this? If your correlation is bigger, slope is getting bigger too, right? The tendency, you see that? And denominator, opposite. If your standard deviation is bigger, your slope is getting smaller, all right? So these values minimize. What is this? These two guys, what is Y minus Y hat? Before we learned this concept is error. And sum of squared error and sum of squared error. Sum of squared error. The sum of the squared residual. Residual is fancy words of errors. So this is too long. So what do you normally say? Sum sum of, it's the same, it's the same, sum of squared error. Inside the parentheses, this is the error. So how many errors? Number of i's. So errors. If we have 300 students, from the beginning, ID 1, Brian, ID 2, Rachel, ID 3, G1, blah, 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 ID 300, J. So the squared residuals are 300s. You have to square each of the error and then sum them up 300 numbers. And the value, the sum value, if the value is the smallest, then the generated regression line is the best fitting line to the chunk of 300 students' data. Okay, what do you mean by generating regression line? Regression line is y hat equals b0 plus b1 x1. So b0 plus b1 is in the y hat. So to generate best fitting line means to generate best fitting b0 and by, because x value and y values are depending on the peoples in the data, right? They are just plug the number of, data collection. And the B0 and B1 are estimated values. Does this make sense? So X and Y, X's and Y's, they are collected data. Let's say you make survey items and you find out Brian, Rachel, G1, blah, 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 until J, 300 students, you have those survey respondents. So you have their answers. You have two variables, X and Y. You have two items, let's say that. So you have 300 data. That is X and Y, X value, Y value for 300 people. And then how can we get B0 and B1? That's not something that we can get from the data directly. That is estimated by the SPSS program based on X and Y collected variable values. Does this make sense? Yeah. So example question is here. Example question. So let's say SAT bubble score X variable is SAT. And then you want to predict the student's college success using GPA, that is a Y variable. But you want to use the predictor SAT entrance exam, SAT. And then outcome variable is GPA. And the given mean of X is 500. Given mean is 2.5. Y is GPA point, mean score, average score is 2.5. SAT is 500, mean score is 500, and the standard deviation is 100, SAT standard deviation, and GPA standard deviation is 0.70. And then R, correlation between two, this is given number, so don't worry about it. Oh, why these numbers are all of a sudden, where are they from? Don't worry about it. The problem maker, question developer just made it up. So they gave these numbers to make you feel hard. No, just this is an example. Just the example. And then from these given numbers, you calculate why. Calculate what? you're going to calculate eventually B1 and B0 to make your best fitting line, regression line. So how do you do that? So we memorize this one right before. Correlation equals covariance divided by multiplication of X standard deviation and Y standard deviation. Okay, so you just simply change this guy, move this guy here, and then SXY equals RXY times SX times SY. So given numbers, you just plug them here, then you got covariance number here, right? Now, covariance number, you know, you use this computational formula, and you can use this here, and then this is what? This is variance, right? So since you already know X standard deviation, covariance is simply this guy. So either you use this one or this one. This one is a little bit easier for me. So why? Because this is a slope, regression slope. Slope regression is based on correlation. So correlation, but regression is more than just correlation. It is the ratio between of the standard deviation of Y to standard deviation of X. So this is kind of intuitive to me. So I can use this one. I mean, if I don't remember this guy, this formula, I just use this one. So 0.65 is here, and standard deviation Y is here, and standard deviation X is here, and then you got B1 slope, you got the B1 0.00455. Then what? When you calculate y-intercept, you just simply use the general form of regression line. What was that? Y equals B0 plus B1x, right? And mean of x, mean of y is penetrate the regression line anyway, right? So you plug this one dot, x of mean of x, and mean of y, and then you have these two numbers and then just plug them in the regression line. Then you got this B0. Then now what you do? Y hat equals B0. B0 is 0.225 plus B1. B1 is here, 0.00455x. Okay. So you got it, right? You got this number here. And then all of a sudden, somebody else just give one single dot here, and then how much it is close to that fitting line. So you got this line will always pass through the mean. Okay, mean, okay. Regression line is here. And then somebody just want to know, you may compute y hat for another x value, say 700. So you plug x, and then what is the estimated y? 3.41. So this is 700 on the x-axis, and then estimated line gives you, just based on this calculation, gives you this number 3.41. But actually, the observed value of y on the x-axis 700 is this guy, right? So there is some kind of distance. There are some distance, right? So that the distances are called error or residuals, right? Okay. Do you have any questions? Please feel free to post questions on the YouTube, okay? All right. Okay, intercept, you can read this one. We have definition of intercept earlier. Yeah, you can read that. Slope, yeah, every 1 point increase in SAT score, we get an increase in GPA of this. Covariance and correlation tell us that the relationship between SAT and GPA is positive. How do you know that? How do you know that? Slope is this positive number. Okay. So correlation, covariance. Correlation, covariance, and correlation. Okay, this SAT score, GPA score, observed data. This is not laboratory experiment data. So we cannot say this is a causal relationship. We just can say there is a correlation relationship, but that doesn't mean it is a causal relationship. So it's just, you have to be careful whenever you use a specific wording. When you use observed data like survey data or students' standardized test scores, when you want to find out some relationship among the variables, they are just correlational relationship, not causal relationship, okay? We will have a chance to talk about causality later. It's very, very important. Yeah. But now we still want to just talk about regression. And regression is based on correlation. Okay. All right. So next class, we're gonna learn the regression analysis step. So preliminary analysis of regression step and how we can go through all the steps in the regression analysis step. That is actually body of this class. Okay, so we will touch this all the concepts later. All right, thank you very much. Bye-bye.